This video is about the binary system and why we use it with ultrasound. The binary system is a way to store digital information. Ultrasound systems are really just computers. Computers work best with digital information. To understand binary, we need to understand the terms analog and digital. Analog refers to any information or signal that can be represented by a continuous variable. The sound of someone's voice is an everyday example of an analog signal. The sound signal that returns to the transducer from the body is also an analog signal. Digital refers to discrete numerical values rather than continuous. The computer cannot write the number, say number 7, like we do. It can only deal with two states, on or off. These states are represented by the numbers 0 and 1. Here's a table of the numbers from 0 to 9 with their binary equivalents. Notice all the numbers can be represented by just zeros and ones in different combinations. Here's a more specific example. The green curve is an analog signal like a sound wave. The x-axis represents time. The tip of each arrow represents the amplitude at a specific amount of time. This is a discrete value obtained from a continuous analog signal. The best way to understand the binary system is to compare it to the decimal system. It helps to remind ourselves that the prefix deci means 10 and the prefix bi means 2. The decimal system uses 10 digits from 0 to 9 and it uses the powers of 10. The binary system has only 2 digits, 0 and 1, and it uses the powers of 2. This first row contains the powers of 10, starting with 0 and then ascending going from right to left. The second row contains the values of those powers. 10 to the 0, or any number to the 0 power, is 1, and any number to the 1 power is that number. And then we have 10 squared is 100, 10 cubed is 1000, and so on. When we want to write the decimal number 4503, we say that it has 4 thousands, 5 100s, it doesn't have any tens, and it has 3 ones. The total value of each column is put in the last row. If we sum those numbers, you notice we get 4,503. We use the decimal system so much that we take this for granted. Okay, let's try writing the decimal number 181 in binary. This time notice that we're taking the powers of 2 rather than the powers of 10. 2 to the 0 is 1, 2 to the first is 2, 2 squared is 4, 2 cubed is 8, and so forth. So how do we get the binary number? We're going to go through each column from left to right. If the decimal number is equal to or greater than the value of the power of 2, we're going to place a 1 in the box below it. Then subtract the value of the power of 2 from that decimal number. If the decimal number is less than the value of the power of 2, we place a 0 in the box and we do nothing else. This will make a lot more sense once we go through the example. 181 is greater than 128, so we're going to put a number 1 in that column. Next, subtract 128 from 181 to get the remainder 53. 53, our remainder, is less than 64, so we put a 0 in that column. 53 is greater than 32, so we can put a 1 in that column. Subtract 32 from 53 to get 21. We repeat the same process for the next column with 16. That results in putting a 1 in that column. Subtract 16 from 21 to get the remainder 5. I'm hoping you're catching on by now, so I'm going to go through the next couple of slides pretty fast. We finally have our binary number for 181 in decimal, and that number is 10110101. We can check that we have the right number by multiplying the power times the binary digit. If we place these values in this last row and add them up, we should come up with the number of 181. And sure enough, when we add these numbers up, we get the decimal number 181. Just a little note, you'll often see binary numbers written like this with 8 binary digits with leading zeros. That's because in the computer they're often grouped in something called a byte, which contains spaces for 8 binary digits. This ends the video on binary.